Imagine driving a car that can go from 0 to highway speed, without ever changing gears. No sudden jolts. No loud engine screaming for the next shift. No complicated gearbox working beneath your feet. Just one smooth, silent push forward. At first, it almost feels impossible. For more than 100 years, gears have been one of the most important parts of every car ever built. Without them, most gasoline cars would barely move. So why have electric cars suddenly abandoned something engineers spent over a century perfecting? Did scientists discover a completely new technology? Or were gears never as essential as we believed? The truth is far more surprising. Because the reason electric cars have almost no gears begins deep inside a machine that spins so differently from any engine humans have ever built. And once engineers understood that difference, the entire automotive industry started changing forever. For over 100 years, gears were everywhere. Cars had them. Trucks had them. Motorcycles had them. Even race cars depended on them. Whether it was a manual transmission or a modern automatic, every gasoline vehicle shared one common challenge. Its engine had limits. Imagine trying to ride a bicycle using only one gear. Starting from a traffic light would feel almost impossible. But once you reached high speed, your legs would spin so fast that you could barely keep up. Now imagine using only your easiest climbing gear. Starting would be effortless. But on a highway, you would pedal furiously while barely moving faster. Neither gear works for every situation. That is exactly the problem engineers faced with gasoline engines. An internal combustion engine cannot produce maximum power at every speed. Instead, it has a very narrow, sweet spot. Below that range, it struggles. Above it, it becomes inefficient, noisy, and sometimes even dangerous. That is why transmissions became so important. They constantly changed the relationship between the engine and the wheels. At low speeds, they multiplied torque. At high speeds, they reduced engine revolutions. Without gears, a normal gasoline car would either stall at the start, or destroy its engine at high speed. For decades, nobody questioned this design. It simply seemed like the laws of physics demanded it. But then, a different kind of machine quietly challenged everything engineers thought they knew. Imagine walking into an engineering lab. On one table sits a traditional gasoline engine. It is filled with hundreds of moving parts. Pistons rush up and down thousands of times every minute. Valves open and close with perfect timing. Fuel explodes inside tiny metal chambers. Crankshafts rotate. Camshafts synchronize everything. Oil pumps, cooling systems, exhaust systems. Every single component must work perfectly. Now look at the machine sitting beside it. An electric motor. No explosions. No pistons. No valves. Far fewer moving parts. At first glance, it almost looks too simple to power a car. Many people assume something so simple must also be weaker. But engineers soon discovered the opposite. And what they measured completely changed the future of transportation. Because this quiet machine could produce something that gasoline engines could only dream of. Full torque. Almost instantly. That single advantage would eventually make one of the most complex systems inside every car, almost unnecessary. But how can a motor with so few moving parts outperform an engine refined for more than a century? The answer lies inside invisible magnetic fields, and it is even more fascinating than most people realize. Imagine standing beside two cars at a red light. One has a powerful gasoline engine. The other is completely electric. The traffic light turns green. The gasoline car hesitates for the smallest fraction of a second. Its engine revs higher. The transmission searches for the perfect gear. Power travels through dozens of mechanical components before finally reaching the wheels. Now look at the electric car. The driver simply presses the accelerator. Almost instantly, the car launches forward. No gear change. No waiting. No dramatic engine noise. Just smooth, continuous acceleration. To most people, it feels like magic. But to engineers, it is pure physics. The biggest difference is something called torque. Think of torque as a twisting force. It is the force that actually turns the wheels. The more torque a vehicle has, the easier it can start moving heavy weight. Gasoline engines are surprisingly weak when they are barely spinning. That is why drivers have to increase engine speed before the car can accelerate properly. This is also why a transmission is needed. The gears help multiply torque at low speeds. Without them, the engine would struggle to move the car from a standstill. But an electric motor behaves in a completely different way. The moment electricity flows into the motor, powerful magnetic fields are created. Those magnetic fields immediately begin pulling and pushing against each other. The rotor starts spinning almost the instant power is applied. There is no fuel waiting to burn. No explosions building pressure. No pistons moving into position. The twisting force is available almost immediately. Imagine pushing a giant merry-go-round. A gasoline engine is like someone who first has to stretch, warm up, and build momentum before pushing. An electric motor is like someone who can deliver full strength the very first second they touch it. That single difference changes everything. Because if maximum torque is already available at very low speed, why would you need several gears to multiply it? For decades, engineers believed every road vehicle needed a complicated transmission. But electric motors quietly proved that assumption wrong. One fixed gear could often do the job. And suddenly, one of the most complicated parts inside a car began disappearing. But there was still a problem. A very big one. Because producing instant torque is only half of the challenge. Cars don't just need to start moving. They also need to travel at highway speeds for hours without damaging the motor. And this is where electric motors revealed another incredible ability. Unlike gasoline engines, they can safely spin at astonishing speeds. Many modern electric motors rotate between 15,000 and 20,000 revolutions per minute. Some high-performance designs spin even faster. That is several times faster than the engine in many conventional cars. Engineers realized something remarkable. If the motor could produce huge torque at low speed, and continue spinning efficiently at extremely high speed, one carefully chosen gear ratio could cover almost every driving situation. From crawling through traffic, to cruising on the highway, to rapid acceleration. All without changing gears. It sounded almost too good to be true. Fewer moving parts. Less maintenance. Lower weight. Higher efficiency. Quieter driving. And smoother acceleration. Car manufacturers suddenly saw an opportunity they had never imagined. By removing the transmission, they could also remove dozens of gears, clutches, hydraulic systems, pumps, and control mechanisms. The vehicle became simpler, lighter, and more reliable. But just when it seemed engineers had found the perfect solution, another mystery appeared. If one gear is so effective, why do some electric cars still have two gears? And why do the world's fastest electric supercars refuse to rely on only one? The answer reveals that even revolutionary technology still has limits. By now, it seems the mystery has been solved. Electric motors produce instant torque. They can spin incredibly fast. And a single gear is enough for almost every driving situation. So why would any engineer add another gear? At first, it sounds like a step backward. But imagine running a marathon. You can sprint. You can jog. You can walk. The question is not whether you can do all three. The question is whether you can do them efficiently. The same rule applies to electric motors. Even though they have a much wider operating range than gasoline engines, they are not perfect. Every motor has an efficiency window, a speed range where it wastes the least amount of energy. Outside that range, it still works. But it gradually becomes less efficient. Now imagine driving on a highway at over 150 kilometers per hour. The wheels are spinning rapidly. To keep up, the electric motor must rotate even faster. At some point, engineers face a difficult choice. Should they use a gear ratio that delivers explosive acceleration? Or one that provides better efficiency at very high speeds? Choosing one usually means sacrificing the other. For most family cars, the answer is simple. Drivers rarely travel at extreme speeds. Smooth acceleration, low maintenance, and long driving range matter much more. That is why companies like Tesla, Hyundai, Nissan, and many others use a single-speed transmission in most of their electric vehicles. It keeps the design simple, reliable, and highly efficient. But performance engineers think differently. Imagine designing an electric supercar. Customers expect breathtaking acceleration. They also expect a top speed that can compete with the fastest sports cars on Earth. Suddenly, one gear becomes a compromise. A shorter gear delivers unbelievable acceleration, but limits maximum speed. A taller gear allows incredible top speed, but slightly reduces the brutal launch that makes electric cars so exciting. Engineers searched for a solution. And some found one. A two-speed transmission. At low speed, the first gear unleashes enormous torque, launching the car forward with astonishing force. Then, as speed increases, the transmission shifts into a second gear. Now the motor can continue accelerating efficiently without spinning beyond its ideal range. To the driver, the shift is barely noticeable. But inside the drivetrain, thousands of engineering decisions are working together in perfect harmony. This is why a few high-performance electric cars use two gears. Not because electric motors need them, but because engineers wanted the best of both worlds. Explosive acceleration. And extraordinary top speed. Yet even this solution introduced new challenges. Adding another gear means adding more parts. More weight. More complexity. More opportunities for wear over time. Engineers had spent years simplifying electric vehicles. Now they had to decide. Was the extra performance worth making the car more complicated again? For most manufacturers, the answer remained no. The simplicity of a single-speed transmission was still one of the greatest advantages of electric vehicles. But perhaps the biggest surprise was still waiting. Because removing dozens of mechanical parts didn't just make EVs simpler. It also made them far more reliable than many people realize. And that hidden advantage may be one of the biggest reasons the automotive industry is changing forever. Imagine owning a car for 10 years. Thousands of trips. Hundreds of long drives. Millions of wheel rotations. Now imagine opening the transmission. In many gasoline cars, you would find a system filled with gears, clutches, hydraulic valves, pumps, bearings, filters, and transmission fluid. Every one of those parts experiences friction. Every one of them slowly wears down. That is why transmissions have always been among the most expensive components to repair. Sometimes a single failure can cost thousands of dollars. Now picture the drivetrain of a typical electric car. Instead of dozens of constantly shifting gears, there is often just one fixed reduction gear connected to the motor. No repeated gear changes. No complex clutch packs. Far fewer moving parts. The difference is remarkable. With fewer components rubbing against each other, there is less friction. Less friction means less heat. Less heat means less wear. And less wear means greater reliability. This simplicity is one of the biggest reasons many engineers believe electric vehicles represent more than just a new type of car. They represent an entirely new philosophy of automotive engineering. But reliability is only part of the story. There is another advantage that drivers experience every single day, often without even realizing it. Think about riding in a traditional gasoline car. As the speed increases, the transmission shifts. The engine suddenly changes its sound. The car hesitates for a fraction of a second before accelerating again. Most drivers have become so used to this feeling that they hardly notice it anymore. Now step into an electric vehicle. You press the accelerator. The power arrives instantly. Acceleration remains smooth and continuous. There are no interruptions caused by shifting gears. No sudden changes in engine speed. No waiting for the transmission to decide what to do next. The result feels effortless. It almost seems as though the car can read your mind. But behind that smooth driving experience is decades of research into electric motors, magnetic fields, power electronics, and battery technology. This wasn't an overnight breakthrough. The first electric cars appeared more than a century ago. Long before modern highways existed. Long before powerful lithium-ion batteries. Back then, engineers already understood one incredible advantage of electric motors. They simply didn't have the batteries needed to unlock their full potential. Only in recent decades did battery technology finally catch up. And once it did, the advantages became impossible to ignore. Suddenly, engineers could build vehicles that accelerated faster, required less maintenance, and eliminated one of the most complicated mechanical systems ever placed inside an automobile. It wasn't because gears had become obsolete. It was because electric motors had solved the very problem gears were invented to fix. That realization changed everything. Today, millions of electric vehicles travel the world's roads with only a single gear. Most drivers never think about it. They simply enjoy the quiet ride, the instant response, and the smooth acceleration. But hidden beneath the floor is one of the greatest engineering achievements of the modern age. A machine so efficient that it made an entire mechanical system almost unnecessary. And perhaps that is the most fascinating lesson of all. History often teaches us that progress comes from adding more technology. More parts. More complexity. But sometimes, true innovation does the exact opposite. It removes what is no longer needed. It simplifies what once seemed impossible to simplify. The absence of gears in most electric cars is not a missing feature. It is proof that engineers found a better solution. A solution powered not by explosions, but by invisible magnetic fields moving with incredible precision. And that simple change is quietly transforming the future of transportation. The next time an electric car glides silently past you, remember, the most revolutionary engineering isn't always the part you can see. Sometimes, it's the part that no longer needs to exist.